Okay, welcome to section 15.9. Change of variable in multiple integral. We know how to evaluate double integral over the region D sine x squared plus y squared dA, where D is the region bounded by x squared plus y squared equal 1. To do this, we just have to convert it to polar coordinate. We call that to evaluate this integral. We convert rectangular coordinate to polar coordinate. Now, it is the same as the changing the variable x and y to be function in terms of on theta. X is the function in terms of on theta is x or theta or cosine theta, y or sine theta. We did this thing before already. We can use the same idea to do the following example. It's double integral over the region D. Sine instead of x squared plus y squared is going to be 9x squared plus 4y squared dA, where D is the region bounded by nine x squared plus 4y squared equal 1. Okay. So if you can look at this problem here, the region D here, there is no way that we can describe in terms of a polar coordinate. Right? So we're going to use a different type of substitution to do this. Cannot be described in terms of polar coordinate. Must find a way to convert region D into a region S so that we can do the double integral. Integral is manageable. The process to convert region D into region S is called change of variable. So here come number 1. Change of variables and the Jacobian. Okay. Well, in order to convert a region D into a region S, right, we're gonna use a one-on-one transformation T. Yeah. Let T be a one-on-one transformation. Where TUV is equal to XY. Okay, and then from here, we see that, well, become UV. Right? Something right here is the region S right here. Right? And then we can use the T. T is one-on-one, so you can go both way, right? So T gonna go this way. You go the other way, it's gonna be a T inverse. Well, right here is gonna be your region XY. Region D, something like this. Region D. Have to rewrite DA in terms of DU and DV. In the region S, cut this into smaller pieces, and then you can get a sample rectangle. I should have write S somewhere. My God. Okay. This sample rectangle here is the polar is UV. You see, it's UV. So that means for the area, just DU and DV. See? So for XY, let's say that we have some point XY right here. Well, we do not have a rectangular area, and we may have something like this, but not exactly rectangle though. We want to somehow estimate this area. We can do so because of the transformation. So the transformation is T UV equal XY. So we can get a vector function, it's all UV. And this vector function would just be it go to the point XY. X is the function of UV and Y is the function of UV. And use the tangent vector to estimate the area of the parallelogram. Right? So here come one tangent vector. The other one is another tangent vector. Right? So use the tangent vector to estimate the area of the parallelogram. Now, once you have this right, you can write out the area. Is If you remember from math 1C, right, the area of a parallelogram is the cross product du or u cross dv of v. Yay, and then we're gonna work it out. Oh my God, look at this thing here. Du dv, they are constant, right? Because they have nothing to do with a cross product. So it's just gonna be a u cross of v du dv. And what is this one? dA. We got dA. Next step is how do we do the cross product of u cross v. You guys remember cross product ij. So what is the RU here? Partial derivative with respect to x. U I. It's not a general though, just regular derivative. But if the function get a little complicated, you got to use the chain rule in here. We also have we have y right here, right? So we got to do a partial derivative with respect to u of y. Reason why I write out ij is because I want to put it in here under the cross product here. RV similarly, right? Partial derivative with respect to v of x. Partial derivative with respect to v of y. Okay. The component of the vector I and the component of the vector j. So it's the partial derivative with respect to x of u, partial derivative with respect to x of v, partial derivative with respect to y of u, partial derivative with respect to y of v. Okay. du dv. Jacobian is the first mathematician to discover this. He used this one. Partial xy over partial uv du dv. And then remember this change in area. So make sure that this is positive because this is part of the area. Make sure that this Jacobian multiple is positive. Putting this all together, we have double integral over a region D fxy dA is equal to, well, double integral over the region S f x uv y uv. The Jacobian. I'm gonna shortcut this thing here because shortcut even further. J. What is J of UV? Because absolute value this thing, the UDV. Now it's pretty cool, huh? A simple example here. Example. Oh, actually, it's a nice formula here. Yeah. Well, we know that if x equal r cosine theta, y equal r sine theta, show that the Jacobian is r. Of this transformation is r. Yeah, I like to use transformation because the transformation comes from linear algebra. If you study linear algebra, oh man, you get a much better understanding of this thing. Okay, so what does this mean? We know that dA, right, is r dr d theta. This r right here, need to show that the Jacobian of r theta r, because it does match up with the whatever I boxed up there, the formula that I boxed, the UV sub. Okay, let's do it. Okay, so we're gonna do Jacobian or theta. Ij. So first one is the partial x with respect to r, right? And partial y with respect to r. Okay, work it out. Taking the partial derivative of x with respect to r, it's gonna be, well, just cosine theta. It doesn't matter which order that you do, right? You can do partial x with respect to r, partial x with respect to theta. It makes your life easy, and then you go to partial y, so you don't have to jump back and forth. Right? So partial x with respect to the radius is cosine theta. Partial x with respect to theta is going to be derivative of cosine negative sine is going to be negative r sine theta. And then partial y with respect to r is sine theta. Partial y with respect to the angle theta is r cosine theta. Okay, so now make sure that you have to do the absolute value of the determinant, right? Okay, so you're gonna let's start r cosine square plus r sine square, right? Make sure that you do the absolute value r cosine square plus r sine square, and it is just r, right? Luckily r is the radius, so yeah, it does match up with the polar coordinate when we do the transformation. where D is the region bounded by the ellipse 9x squared plus 4y squared equal 1. Okay. So you got to figure out the substitution. What would be the u and the v here? So we can turn this thing into a nice region. Actually, let's make it a little bit more cool than by the ellipse in R1 in Q1. Yeah, it's easier for me to sketch. I don't have to use the. Okay, so here comes your region D, right? It's gonna be so if you let y equal to 0, then it's gonna be x equal 1/3. So 1/3. Oh, 1/2 is bigger than 1/3. 1/2, 1/3. So that you guys get a visual of the region D. Okay. Well, we know that we cannot evaluate the double integral in this region D because there's no way that we can use polar coordinate for ellipse. You got to use the transformation here. Let u equal v equal anybody. Nine x squared look like it's the 3x to the power 2, right? So you can let u to be 3x and v to be 2y here. Then what is going on here? U square plus v square is 1. Nine x squared plus 4y squared equal 1. So u square plus v square equal 1. That means 1, 1. A part of the circle. Your region S here, right? Okay. So now we just got to figure out the Jacobian. In order to figure out the Jacobian, we got to solve for x and y. Because the definition of the Jacobian, look at this one here. You got to know what x equal to, what y equal to. So from here, we get x equal to 1/3 u, y equal 1/2 v. The Jacobian, very important. Get this thing first before you do the setup. Jacobian uv is ij. I think you write this thing up a few times and it's gonna just stick to your head. Okay. Ij, work it out. partial derivative of x with respect to u is 1 over 3. X with respect to v, there's no v here, so it's going to be 0. Y with respect to u, there's no u, so it's going to be 0. Y with respect to v is 1 over 2. Yeah. Okay, so sine of 9x squared plus 4y squared dA, right? Equal to, I'm going to call it a UV sub here. Well, once you do the UV sub, it will be a double integral over the region S, sine of u squared plus v squared. And then the dA is going to be the Jacobian multiplied to d u dv. So that would be we know the Jacobian here. I'm just going to multiply by 1 over 6 du dv. Okay. Now, does it look good? The region S there is du dv, right? It's equal to r dr d theta. And then the radius r is going to be between, the angle theta is going to be between, manageable. Sine of, r squared times 1 over 6. R dr d theta. Oh, integral is 0 to pi over 2 d theta, integral 0 to 1 r sine r squared dr. Yeah. 1 over 6 times pi over 2 multiply 2. Okay, so 1 over 2 integral of sine is negative cosine. Yeah. 6 times 4 is 24, so it's pi over 24. That number 4 is too small. 1, so it's going to be negative cosine of 1 minus negative cosine of 0. Okay. Cosine of 0 is 1, so it's going to be a 1 minus cosine 1. So pi over 24, 1 minus cosine 1. That is it, because I don't have a calculator. It's good enough answer here.